Okay, so welcome back, grade 10s. We're kind of in the home stretch here before the end of the year. So we're just going over the next type of compounds, which is covalent compounds. So last week we went over ionic compounds, which really is only a very small percentage of the world. It's really just the rocks, salts, and crystals. But if you look at most of the world, it's not an ionic compound. Most of them are not these rocks. They're things like books and wood and people and animals and plants, and all of those are all covalent compounds. So that's what we're going to talk about today. It's a much larger class of molecules. So we'll start with just kind of recapping. So elements form compounds to be reactively stable. Okay, and why they're reactively stable is because when they form a compound, both elements have a full outer ring. Okay, so with a full outer ring, no valence electrons are available to jump. Now, there's really only two types of compounds that we can form from elements. The first one we talked about last week, which was an ionic, and that's when you take a metal element and bond it with a non-metal element to make a compound. And again, those are very simple compounds. They're all really the same, just the rocks and salts. Now, the other type of compound you can make is called a covalent. And that's when you take two non-metals and bond them to form a compound. And that's what we're going to be talking about today. Now, there is another type that's not really a compound. That's when you take two metals and you put them together. But it's not really bonding, and we call them alloys, but they're not compounds. There really only is two compounds, ionic and covalent. So ionic compounds were covered last week, and they're much easier to understand than covalents because they're basically all the same. They're a rock, salt, or crystal. They're all solids. They're all brittle. They all dissolve in water. They don't really react with anything, so they're really similar. But when we get to covalence this week, they're much different. They're not all the same like ionic. Some are solid, some are liquid, some are gases, some are reactive, some are not reactive. Some are flexible, some are brittle. They're all over the place. They're much different. So let's try and get into those today. So the basics of covalent compounds. So these compounds are what, when we say the word molecule, that's what we're referring to as a covalent compound. If you say the word molecule correctly, you're not referring to an ionic compound. It's only covalent. Because a molecule kind of defines an actual little space here. So let me kind of look at our picture up here and the right. This is a molecule of water. When we talked about ionic compounds, you would have 100 sodiums and 100 chlorines and it's still salt, or 50 sodiums and 50 chlorines and still salt. In covalent compounds, it's much different. They have defined numbers, so you have to have 2 hydrogens and 1 oxygen. Anything other than that, it's not a molecule of water. So this is what we consider a molecule, a single kind of particle of a compound. Now the other big thing is the formula represents the actual number of each element, unlike ionics. Remember when we wrote the formulas for ionics, it would be like NaCl. Okay, well that means 1 sodium and 1 chlorine, but it really could be 100 sodiums and 100 chlorines. It's just telling it's a 1-to-1 ratio. But when we do actual covalent compounds, and we write something like, say, H2O, we're writing that there's 2 hydrogens and 1 oxygen, and that's fixed. Okay, it's not a ratio, it's the actual number of elements. And there's our hydrogens here, and there's our oxygen, so H2O. Now, covalents are not really similar like ionics. Covalents can be gases. So if you see a gas at room temperature, you know it's covalent. They can be solids, so you wouldn't know whether it's covalent or ionic. But if you see a liquid at room temperature, for sure you know it is a covalent, like water or ethanol or acetone or oil. Okay, all of those are covalents because they're liquids. Some can be brittle, some are flexible, some are soluble, and some are not. So they're really variable. Okay, they're not like covalents that are all the same. And that's why we teach them second, because they're a little bit more expensive. So most of the world is not a rock or a salt or a crystal. So most of the world is, in fact, made up of covalent compounds. They're a lot bigger class. Covalent compounds are formed by covalent bonds. So we want to kind of look at, well, what is a covalent bond? Because it's much different than an ionic bond where you give an electron and somebody takes an electron. In a covalent bond, it's going to occur between 2 nonmetals. But the big thing here is that they share electrons. In ionics, the metal gave the electron to the nonmetal because nonmetals want electrons. But if you have 2 nonmetals, like in a covalent, nobody's willing to give it up because they both want electrons. So the only option is sharing. And that's a big difference between ionic and covalent. They share electrons. So when 2 atoms form a covalent bond, the sharing of electrons allows both atoms to satisfy the octet rule. So if we look kind of over here at F2, or fluorine, a fluorine molecule. Fluorine normally has 7 electrons in its outer ring, so I'll do the 7, right? 1, 2, 3, 4, 5, 6, 7. That was that fluorines. And then I'll do the other fluorine 7 in the other color. 2, 3, 4, 5, 6, 7. So neither can give up an electron. One fluorine can't give up the electron to the other fluorine, but what they can do is they can share. So the two that I'm kind of highlighting in yellow are the electrons that they're sharing between each other. And when they share them, they each have a full outer ring. Okay? And that's a big difference between ions. Now, here's an also big difference, is when you share, okay, you can form these things called multiple bonds. So covalent bonds, because they share electrons, unlike ionics, can be single, double, or triple, depending on the number of pairs the electrons are sharing. So if we look over here at, say, water, okay, in here it's a single bond. So this is just a single bond between between oxygen and hydrogen. Two single bonds. The one single bond between hydrogen and the one single bond between the other hydrogen. Now, other molecules, so right here we're actually only sharing 2 electrons here. Okay, that's called a single bond. But if you share 4 electrons, like over here in the middle one, like if you take an oxygen molecule, they actually have to share 4 electrons. Then we call that a double bond. And this can't exist in ionics because they don't share. But when you share, you can have double bonds. Sometimes if you share 6 electrons, like nitrogen, okay, that's a triple bond. And again, these don't exist in ionics, they only exist in covalence. But having double bonds and triple bonds makes it very difficult to predict the formula of a covalent compound, which we'll be getting up to. So some really popular covalent compounds that we should know are called our diatomics, or our gases. And they're really kind of just a molecule that's an element that's bonded to another element of the same type. So we call these the super 7 or diatomics. These elements always bond to each other, forming a covalent bond and never on their own. So if you take something like hydrogen, okay, and you try and take a single hydrogen atom, it will immediately bond to another hydrogen atom. Okay, same with a nitrogen. If you have a nitrogen atom, it'll just immediately bond to another nitrogen atom. Same with oxygen and fluorine and iodine and bromine and chlorine, and we call these the super 7, okay, because there's 7 of them. 1, 2, 3, 4, 5, 6, 7. Now, other molecules don't do this. Okay, so something like iron or carbon or nitrogen's a bad example, but sodium. Okay, sorry, I have a typo there. That shouldn't have nitrogen in there, so I'll put that one in red. And sodium. But these molecules right here, like iron, carbon, and sodium, they can all exist on their own. You can have a single atom of them. They don't spontaneously start bonding with each other. Okay, but when we have something like these elements over here, they just automatically bond with each other. So diatomic molecules, the super 7, can never exist on their own, but only in a covalent compound. So you can never have N1. It's always N2, or O2, or F2, or Cl2, or Br2, I2, or H2. Now that's when they're on their own. If they come into a formula, that you could have a single one. Like you could have a single nitrogen in a formula or in a compound, but as soon as they're on their own, they automatically bond with another of themselves. Okay, so now we're going to go through some properties of covalent compounds, and these will be a little bit trickier than ionics because, again, they're a lot wider range. So in covalent compounds, they have a broad range of properties compared to ionic compounds. When we look at their physical properties, they can be a solid, liquid, or a gas. Okay, they can be all three, where ionics can only be solid. So if you see anything out there that's a liquid or a gas at room temperature, you know it's covalent, because ionics can't be that, but a solid, you wouldn't know whether it's covalent or ionic. Now, some covalent compounds can dissolve in water, but some can't. Okay? Sugar is an example of a covalent compound that can dissolve in water, but then CO2 is one that can't. Covalent compounds that can dissolve in water, like sugar, don't conduct electricity because they don't have any metals in them. So if I take water, so pure water, we've been taught in the past, actually conducts electricity. Well, that's not actually true. Tap water does, because tap water contains not just water, but also many other things dissolved in it. But if you have pure spring water, like pure H2O, it won't actually conduct electricity because there's no metals in it. It's only hydrogen and oxygen. The only way you can have water conduct electricity is if you dissolve things like sodium or calcium. And those are the kind of things that are in our tap water. Okay, now some of the chemical properties of covalence, again, much different than ionics. They're much more reactive than ionic compounds. Okay, they will react with a lot more things than ionic compounds will. All of our fuels and explosives are covalent. If you're going to make a bomb or a fuel like gasoline or propane, they're all going to be covalent because they're a lot more explosive than ionic compounds. Now, there is some, though, that are unreactive, like a diamond. And so a diamond looks like it might be ionic compound. It's a crystal, but it's actually covalent. But other things are very, very reactive, like nitroglycerin, okay, which is a very, very reactive liquid. So here's just some common examples of covalent compounds. We've got ammonia, which is nitrogen and hydrogen bonded together, two nonmetals. Hydrogen gas, water. This is propane. You may have heard of this before. Okay, this is what your barbecue probably runs on, or if you live in the country, you might heat your house with this. And again, it's just carbons and hydrogens, two nonmetals. Butane, if you've ever used a lighter before, that's what's inside a lighter. It's just 4 carbons and a whole bunch of hydrogens. Pentane, probably not very familiar with. You might be familiar with octane, which is just a few more carbons in this, and that's what's in gasoline. Here we have hydrochloric acid, okay, another covalent compound. So the hydrogen and chlorine, both nonmetals. Here we have carbon dioxide. So we've got 1 carbon and then 2 oxygens, and that's where the dioxide comes from. So di means 2, so carbon dioxide. Then over here we've got carbon monoxide. So 1 carbon and 1 oxygen, so carbon monoxide, and this is a very, very dangerous gas that can kill you. Okay, the next thing we're going to go through is just now how we name covalent compounds. And this is a little bit different than ionics, but it's not a really tricky one. Actually, some people really prefer it. The key is that we're going to be naming them using what we call the IUPAC naming system. Now, it's not really important, but the IUPAC is what the entire world uses to name chemicals. It's called the International Union of Pure and Applied Chemistry. That's what IUPAC stands for. And basically, the whole world has to use the same nomenclature. We can't, some of us call hydrochloric acid, and then another country call it chlorine or something like that, something different. It all has to be the exact same. So that's the naming system the whole world uses. Everybody uses the same naming system. So we're going to teach you how to name covalents. Now, before we get into that, we have to know what prefixes are. So just kind of some short terms for what they mean. So when you hear the word mono, that means 1. Okay. Di means 2. Tri means 3. This is probably some new ones. Tetra is for 4, and penta means 5. Okay? And these are the ones that we'll be using. There are some bigger ones, but we're just going to be using the ones 1 to 5. And we're going to be using these in the name. Okay? Like carbon dioxide, you can probably already see the di in there. So how we name? So we're going to start by saying, okay, let's name this thing right here. NS3, 2 nonmetals, makes covalent compound. Well, the first thing we do, step 1, is we name the first element in the formula. Right? So we look at the periodic table, and that's nitrogen. So that's what I'm going to start with, is nitrogen. There's step 1. Okay? Now I'm going to go to a different color here. Step 2 is I name the second element. Well, I look in there, and that's sulfur. Okay? So I've just done step 2. Named both elements, nitrogen and sulfur. All right, now I'm going to go to a different color. What about step 3? Step 3 is replace the ending of the second element with "ide." So we're going to change sulfur to sulfide, just like we were doing in ionics. So really, this almost looks like an ionic name right now, nitrogen sulfide. But here's the key, and this is the last step, and this is what really separates it from covalence, is we add prefixes to represent the number of each type of atom. And we don't use mono for the first name. So the first one, we have nitrogen, and we only have 1 of them. So if it was the second name, then we would have to put mono in there, but we're just going to name it nitrogen, okay, because there's only 1 of them. And since there's 3 sulfurs, we call it trisulfide. So nitrogen trisulfide. So let's go through a couple more examples. If we look at here, okay, let me just get my pen out here. And I want to name this. Well, the first thing I'm going to do is name the first element, carbon. Okay. Then I'm going to name the second element, which is oxygen. But I'm going to change it to oxide because we never use just on the second part. Their name. So carbon, oxide. Now I have to look at numbers. Well, I only have 1 carbon. So I could call it monocarbon. But if the very first element has only one, we usually just leave that mono out. And I have to look and say, well, how many does oxygen have? Well, it has 2. So I put in the term for 2, carbon dioxide. So what this is telling me is that this is 1 carbon, and then the dioxide would be O2. And that's how we call carbon dioxide. If we looked at here, so here's one where there's actually 2 of each one. So always start the exact same way. So nitrogen, and then that's sulfur, but I'm going to change it to sulfide. Now I have to look and see, well, how many nitrogens do I have? Well, I have 2, so I would put it as di-nitrogen, and then how many sulfurs? 3. Tri. Dinitrogen trisulfide is the name of this molecule. So a couple other ones right here. You can try these on your own, but we've got carbon. And then there's an oxygen on there. I'm going to change that to oxide, and I only have 1. So this is carbon monoxide. Monoxide. Okay. Here we've got phosphorus and oxygen. So this is diphosphorus trioxide. Okay. Down here I only have 1 sulfur, so this is going to be, and I could call it monosulfur, but again, we usually don't use that term at the very beginning, the first one. It's not wrong if you do, but we usually don't. So this would be sulfur trioxide. And down here I've got 2 nitrogens, so dinitrogen. Sorry. And then 2 oxygens, dioxide. Okay? We don't have to put these dis and tris in ionics because there's only one set formula. Now, when we do the crisscross rule, the formula is for sure that. But when we use covalent compounds, we can't use the crisscross rule. So we don't actually know what the formula is just by saying, well, if carbon and oxygen come together, it can make carbon monoxide or it can make carbon dioxide. And that's why we have to make sure that we use this term in here in covalence, because we don't know which one it made, whether it made the carbon dioxide or carbon monoxide. In ionics, there's only one option, but in covalence, there's not. Okay, so just finishing up here on covalence, there's a couple things that we should know and just some common names. So CH4, okay, now if you were to name this, it would be carbon tetrahydride. Okay. But there's also some more common names. So this is, as a chemist, this is what we would call it. But most people are not chemists, so they're not going to be calling it this. They're going to call it things like natural gas, okay, or methane gas. So that's the exact same thing. CH4 is really just natural gas or methane gas. NH3, if we named this as a chemist, we'd call it nitrogen trihydride. But again, most people are not chemists, so they call it ammonia. Okay. Water is what we call it, or most people call it. As a chemist, you would call it dihydrogen monoxide. And then this one down here, C6H12O6, okay, kind of a bigger molecule, but again, a whole bunch of nonmetals. And this is what sugar is, okay, or table sugar. It's just carbon, hydrogens, and oxygens combined together. And to be honest with you, this is what you are primarily composed of, is combinations of sugars, fats, and proteins. Okay, so the last thing I want to talk about was formula generation. I've kind of already alluded to it. Now, when we went through ionics, we had a whole kind of lesson on making formulas for ionics because they're set, and there's not really multiple different formulas you can make. So in ionics, you could get 2 elements, and using the crisscross rule, you could develop the formula. Okay? However, when we get to covalence, it only sometimes works for covalence. So you can use the crisscross rule, and it will work sometimes, but not all the time. So since covalence can make double and triple bonds, it's hard to predict the formula of a covalent using the crisscross rule. When we get to grade 11 chemistry, it's going to teach us how to develop these formulas. But for grade 10, we don't need to really know at this point how to develop the formulas, but knowing that there's multiple different formulas that can develop when you take, say, carbon and hydrogen and put them together. Okay? All right, so that's it for this lesson on covalence. Next week, we're going to be kind of closing up. We're going to be talking about reactions. And then that'll be it for the last 2 weeks, is kind of showing us how we do reactions. Thanks, guys. Good luck.